Hello everyone, this is Dr. G. Karthik Reddy working as Associate Professor in the Department of EC, MLR Institute of Technology, Hyderabad. Today's session topic is properties of power spectral density. What are the properties with proofs we are going to discuss in this session? Okay, mostly we will discuss the properties of power spectral density. Okay, first property tells that power spectral density is always non-negative. Okay, from the statement, what is the definition? Power spectral density definition is limit t tends to infinity expectation of mod xt of omega whole square by 2t. Since we are always the mean square value is always mod of xt of omega whole square is always non-negative. When the mean square value is always non-negative, then the definition is also non-negative. Therefore, always the power spectral density we are going to get non-negative value. Now, next second property tells that x of t is real. X of t is real. Xx of minus omega is equal to xx of omega. Means satisfies the symmetry property and it is a even symmetry property. Even symmetry property. Xx of minus omega is equal to xxx of omega. You know the definition. Xxx of omega is equal to integral minus infinity rxx of tau e power minus j omega tau theta. Okay, you do the proof. Xx of minus omega which is equal to integral minus infinity rxx of e power j omega tau d tau. Let us consider tau equal to minus tau. Then what you are going to get? Integral minus infinity rxx of tau minus tau e power minus j omega tau d tau. Now we know the property from the autocorrelation function that rxx of minus tau equal to rxx of tau. Okay, from the even symmetry property of autocorrelation function. Then substitute that, then compare the relation of equation 1 and equation 2. Okay, compare the relation of equation 1 and equation 2. Okay, here what you are having? You are having the relation, then what is any difference you are having? No. Then what you have to do means you substitute here rxx of minus tau. Okay, then what you are going to get? Here in place of tau minus tau, if you substitute, or e power minus j minus omega. Okay, minus omega or minus omega minus tau. Then you will get the resultant answer. Xx of minus omega is equal to xx of omega. Means here it is satisfying the even symmetry property. Now next, here is telling that third one, it is real. When it is real, real quantity, because you are having the definition. This is the definition of power spectral density. Then from the definition, if it is non-negative and when you apply the modulus, then you are going to get only the real quantity. Then here always the power spectral density is non-negative and its real quantity. Non-negative and real quantity. Now next, here this is the definition of average power. Okay, you know the proof. Average power is equal to area under the curve of power spectral density. Area under the curve of power spectral density is the average power. Okay, which is Pxx. Okay, which is equal to A is a time average of expectation of x square of t. Okay, now this one we already done that. Okay, xt of omega, this is Fourier transform relation. Now apply the conjugate of that. Now apply the substitution conjugate on both sides. Okay, then you apply, then what you are going to get? xt of minus omega and xt of minus omega conjugate. Then you can substitute then xt of omega conjugate into xt of omega is xx of omega. Means xx of minus omega is equal to xx of omega. Okay, this one proof of this one. Okay, proof of this one, we have solved this one. Okay, proof of the second one. Okay, you can use the Fourier transform pair by using that relation of average power concept, average power and power spectral density. Then you are going to get the resultant, okay, which is an even symmetry. Now next, we are having next property xx of omega is equal to omega square into xx of omega. Okay, or means here we are having this xxx. Here we are having the differentiation of that. X dot represents differentiation of x of t. Okay, differentiation of x of t are considering as x dot dot. Okay, d by dt of x of t. D by dt of x of t means the differentiation we are taking with respect to some particular point. Okay, some particular instant. Okay, limit x epsilon change. Okay, this is the definition of the differentiation term. X of t plus small change minus x of t by small change. Xt of omega, this is a apply that in the definition, which is for the interval defined from minus t to t. Then xt of t. Okay, substitute that. If you are having f of t minus a is equal to f of omega e power minus, this is one of the property of Fourier transform. Then you substitute that xt plus omega you are having, that is xt of omega e power j omega epsilon. Okay, then you are going to get the resultant is j omega xt of omega, j omega xt of omega, j omega xt of omega. You have to substitute in the actual definition. This is the definition of power spectral density. Okay, xx of omega is equal to limit t tends to infinity expectation of xt of omega whole square by 2t. But here LHS part you are taking x dot dot. Okay, x dot dot you apply for x dot for this, which is equal to x dot of xt of omega. Then what you are going to get? J omega xt of omega whole square by 2t. Now next, when you apply the absolute value, okay, j term will be neglected. Omega you take outside, then you will get omega square. Limit t tends to infinity. Expectation of xt of omega whole square by 2t. Okay, this one, this portion we know that this is the definition of power spectral density, that is xx of omega. This is a fifth property. Statement tells that differentiation of x of t of the power spectral density is equal to omega square into power spectral density. This is the differentiation of the x of t of the power spectral density. Then we are going to get the, this is a relation. This is also one of the property of power spectral density. Okay, here we discuss the 5 important properties of power spectral density. One is, first property tells that, just summary of the today's session. First property tells that power spectral density is always non-negative. Next, if power spectral density is a real quantity, it satisfies the even symmetry. It satisfies the even symmetry. Now next, we are having one, next, the real part of power spectral density. Real part of the power spectral density is always satisfies the even symmetry, and the imaginary part of power spectral density is always satisfies odd symmetry. This is the extension to this second property. Okay, the real part of power spectral density satisfies the even symmetry. Imaginary part of power spectral density satisfies the odd symmetry. Now next, here, okay, now this is a next, the power spectral density of the differentiation of x of t. Okay, differentiation of x of t, or the x of t differentiation of that of the power spectral density is equal to omega square into xx of omega. Okay, these are the important properties, and along with that we are having one more property, that is autocorrelation function and power spectral density form a Fourier transform field. Okay, form a Fourier transform, or we can also tell that time average of autocorrelation function and power spectral density form a Fourier transform field. Or we can also tell that this relation is called WK relation or Wernier-Kinchy relation. Okay, this concept we are going to discuss in the next lecture. This is also one of the property of power spectral density. Total 6 properties we are having. All these properties are useful while we are solving for the numerical problems related to the power spectral density. Okay, these are the topics we have discussed for the today's session. In the next session, we are going to discuss the relationship between autocorrelation and power spectral density. Thank you.